Hello everyone. In this webcast, we're gonna talk about the problem-solving strategies using conservation of energy. The first learning objective after watching this webcast, you'd be able to develop a formula sheet, and you'll be able to explain the application of conservation of energy. So when you have to or you can apply the conservation of energy, and how do you know in general cases, not the special cases, how do you know in general cases that this is the problem I should be using conservation and energy? And you should be able to follow those guides and solve a step-by-step problem using conservation of energy. But here, for the list of the formulas, the conservation of energy is T1 plus V1 and T2 plus V2. So what's T and what's V? So T is the kinetic. It's represented by half mv square. M is the mass and V is the velocity. V and this capital V is the potential energy, and which is depends on height. It is represented by mgh. So what do we mean by 1 and 2? So 1 represents an initial condition. It could be A, B, or any point. So initial, so final condition and initial condition. If you have the spring in your problem, you have to use the elastic potential energy, that is half k s squared, where k is the spring constant and s is the distance. And most of the time, the most equation that you have to use in solving problem using conservation of energy is that equation of. So this is our list of the formulas. So let's move to the next step, which a general understanding that will cover most of the concept that you need to solve most of the problem that in your textbook. Energy, if your particle as it, so your potential kinetic energy is 0, and also we know that the potential energy V, it depends on height mgh. So if you have a datum or the base or the ground, if h is 0, your potential energy is 0. So you have to understand this concept, because you may have to use these boundary conditions in your problem to make the problem simpler. Also, another concept that you need is that a pendulum motion. So the highest point, this is the lowest point, and this is our highest point. The highest point could be up here where it stops and goes back. This is your highest point. The highest point here, when it stops and goes back, the energy is entirely potential, because it stops here, it's going this direction, it stops and it starts to go back. So at that highest point, the energy is entirely potential, the distance of the height, and the tension on the cord is minimum. The tension is minimum because when you are at highest point, the weight is downward, and then the tension is minimum. When at lowest point, when you are down here at the lowest point, you are gaining velocity each second, and this is maximum at lowest point. So at lowest point, energy is entirely kinetic, and since this is our datum, your h height would be 0. So there is no kinetic, there is no potential energy, entirely kinetic energy, and then the tension on the cord is maximum. Another concept that we need to understand, that normal reaction is 0 when no surface contact. For example, if you have a path and there is a car moving in this direction, so if it's if it's about to fly off the track, at the moment of the fly off, there is no contact with the surface or the ground, so no contact. At that point, you have to assume that the normal force, normal reaction at that point, whatever point it is, nx or na or nb, equals to 0. This is a concept that it will simplify your problem, or you may have to use it if there is a condition that says the normal the car or the box will jump off the track, or it should not leave the track. In this kind of scenario, you can apply this concept. Now let's talk about when we should apply this conservation of energy. How do we know that this is the problem that where we should apply conservation of energy? Conservation of energy includes, so if your motion is kind of on xy plane, or there is a vertical displacement happening of any particle in any direction, so vertical displacement happening, that activates gravitational acceleration. So this is a condition where you should think that this might be a problem where I should apply the potential energy. So we know the height and we know the path. It's moving in xy plane, so gravitational acceleration is activated. So this scenario we can apply conservation of energy. Another scenario is that motion path is given. So if you see in a problem where the path of the motion is given, for example, this problem, the path of the motion is given, so that this box will walk through this way, this spring can go this way, the pendulum will move this direction. The path is given, and 2 points, initial and final point scenario, meaning if I have, for example, a roller coaster, I have point 1 A, and another point maybe here B, and another point here C. So the good thing about potential conservation of potential energy is that it can be applied in any 2 points. So 1 point here, 1 point here, between 2 points, 1 point here or another point. So an initial point condition is given, and final point condition we are asked for. So final point, the condition, the question is asking about the condition at final points. So if you see 2 point scenario, this is also an potential problem that you can apply conservation of energy. Condition is that active forces are conservative. To be able to apply the conservation of energy, you should be able to know that all the force that are acting is conservative. What that means is that if you see in a problem, this is there is no friction, avoid air friction, this is a sign sometimes is that it tells you it's a conservative force scenario, and you may apply, and you can apply potential conservation of potential energy. Also, the problem must involve velocity and displacement. Why? Because to apply conservation of energy, you need velocity. So if your problem doesn't have velocity condition or displacement, which is height, you cannot apply this equation. So these are the condition you need to check. If those are available, you can apply conservation of energy. So now we'll see an example, and we'll walk through how the thing that we have learned so far can be applied to a problem, to solve a problem step by step. Pause in the video and then ask yourself the question, and maybe you can re-watch the video up to this point to take notes, and once I tell you about the problem that we're about to solve, you try yourself first and then go through step by step. So let's see what the problem is. So see, the problem says there is a box here that follows a path, roller coaster path, and it goes down and then it becomes flat. So a box is traveling this path, and we have points named. This is point A, this is point B, and here at the junction of curve and the flat line is point C. The height, so this is the path. The height here is given. This height to the datum here is 20 meter. The question asks you to find the height from top to the base, which is h, and also it asks for the velocity at point C, so VC. So the questions are the box A at point A starts from rest, so rest at A, point A, and it starts from there. The problem says the box, when it travels, it doesn't, we have to design in a way that what would be the height h, so that the box doesn't leave this track. So at point B, at B does not leave track, and the problem also says find the velocity at point C. So what is VC, and what would be the h? H equals to what, so that the at point B the box doesn't leave the track, and what is C. And then the fourth point the problem says is that neglect friction. This is also given the radius of curvature at this point, which is 7.5. So I would like you to pause here and think about the problem and go and rewatch the condition that we have talked about in the previous slides and see if you can approach this problem. So first, let's see if this is a problem where if we can apply conservation of energy. So one thing, first it says neglect the friction, so it's most likely there is no non-conservative force, so all forces are maybe conservative, so we apply. It also, the path we talked about, if the path is given, so here the path of the box is given, so it's also a second condition that we may apply. The problem says about 2-point condition. For example, the problem says the condition at A, which is the box is at rest, and it asks about the condition at point B, so this is 2-point scenario, and also it's asked about the condition or velocity at point C. So again, it's a point C or B or A or C, so again it's a 2-point condition, so we may still apply the potential energy, conservation of potential energy. Also it meets the first criteria, which is the box is moving in z direction or vertical direction in xy plane, so z is activated, so we can use the potential energy. It satisfies all the conditions that we talked about about using a conservation of potential energy. So let's see how we can solve the problem. So my first step would be just writing the conservation of energy. We know that TA equals to half mVA square plus mgh, when m is the mass of the box, which is not given, so we'll assume m is the mass of the box, would be equals to half mvb square plus mghb. So in this equation, what are the things that we don't know? We know that the box starts from rest, so VA is 0, which is this term becomes 0. We are looking for H, and we know the mass is M. Normally it will be cancelled out from both sides. If we divided M by both sides, it will be cancelled out, so we'll be left with GH. And if we write down half VB square plus G HB, so HB here in this equation, HB is the height of the B here, which is known as 20. So we know this is 20. We know G, we don't know VB, we don't know H. So we need to find either of the one to activate this equation. So now we go back to the problem and see what are the if the problem has something to say. So if we look at the problem, we saw that in the problem says that the box, when it moves, it should not leave at point B. What is the condition that will satisfy that the at point B the box doesn't leave the track? When the box leaves the track, there is no contact surface with the track, so the normal reaction force at point B and B would be equals to 0. That's what we already talked about. So now we're going to use this condition and apply to find VB. So now we're going to draw the free body diagram at point B. So at point B, I have my box upside down, and there is no track because it's about to leave the track. So there is the normal force, normal reaction force at point B here, and B is 0 because it's about to leave the track. The weight is always activated, so weight, which is mg, and there is also tangential force because the box is moving, so but we're not interested in the tangential part. So we're gonna use, we also talked about that most of the time we have to use equation of motion. So equation of motion, so which we know is summation of F equals to ma. Since we're working on the normal side, so we'll use mn for our benefit. So we're going to take the force in normal direction. So the normal force are mg, the weight, and also there is mb and b, the normal reaction, but that is 0, and there is also always mass. And for an, we know an equals to v square, vb square over rho b. We know rho b is given, which is 7.5 meter. M can be cancelled out. Z we know, so we can find vb. If you solve for vb, you will find that it is 73.6 meter per second. So now we can use this VB back to our previous equation here, plug it here, and we can find H. And if you do that, you will see that your H is 23.75 meter. Pause pause in the video and work it out and check if you can find this answer. Now, so this is our one condition, that we need to find H, and we found H. The question also asks us to find velocity at point C, VC. What is VC? So again, to apply conservation of energy, we need 2 points. Now we're going to select point B and point C. So we're going to apply the equation at point B and C. So this is our equation of conservation of energy taking point B and C. So kinetic portion, potential energy, kinetic energy at C, potential energy at C. So at point C, when the track is flat, so H is 0, so this entire part becomes 0. We know HB, which is 20. We know what is Z. We know M would be cancelled out. If you divide both sides with M, it would be cancelled out. We know the VB. VB we just figured out, find out, and which is 73.6, and we know, so only unknown is VC, and if you find VC, your answer would be 21.6 meter per second. So I would suggest that you pause and do the calculation yourself and check the answer. After checking that, you take your note and open your textbook, pick up any problem from the exercise and follow the same step, follow the same condition that we say, that if this condition matches, you can apply the conservation of energy, and try yourself. And if you have any question, you can always comment and I'll reply back. I hope this helps for you to prepare. So see you in next video. Till then, thank you.